Hey guys, today we're going to be covering projectile motion. If you have not seen the previous video that covers vertical motion or free fall in the vertical direction, I would suggest that you pause this video and go back and watch that one now. We are going to be assuming a few points that video lays out. To recap that video, three basic points that you need to know are that first off, projectile motion, by definition, is when the only force an object feels is due to gravity. On Earth, even though a falling object feels other forces such as air resistance, that is considered to be negligible, and it's considered that the only force acting on those objects is the force of gravity. The second main point is that because gravity is the only force acting on it, the only acceleration that an object feels is due to gravity. And so that's going to be g, or 9.8 meters per second squared, in the downward direction. For this video, we will be assuming that down is negative and up is positive. And so this means the acceleration due to gravity is going to be negative g, or negative 9.8 meters squared. So previously you guys dealt with horizontal motion, moving across, back and forth, cars driving, people walking, motion in this plane, in the horizontal plane. And in the last video you dealt with vertical motion, moving up and down, free fall, projectile motion up and down only, drop a ball off a building or throw a ball up and down. Now we're going to be dealing with diagonal motion. And in this case, we're actually going to be dealing with motion both horizontally and vertically. Because of this, it's actually very similar to what you've done in the past, both in the last video and previously with horizontal motion. The only difference is now you're going to be solving for both the horizontal and the vertical concurrently. The variable we usually deal with when breaking down into horizontal and vertical components is the velocity. Usually you have an initial velocity, somebody throws a ball at some angle. You have an initial velocity at an angle. And so usually you take this diagonal velocity and you usually break it down into a horizontal and vertical component. Horizontal. Now technically we could break it down into components in any reference frame we want. We just do horizontal and vertical because it tends to be the easiest and also most intuitive. Horizontal is along the ground, vertical is up and down. When it comes to this example, this little example here that I've drawn out, I have a little cannon shooting a cannonball off at this angle. We are going to have, because I said moving down was negative, moving upward is going to be positive, so positive wise that way. And horizontally, generally speaking, moving away from your source is positive. So if I'm throwing a ball or my cannon is shooting a cannonball, motion away from me as I throw the ball is positive horizontally. And so I'm going to have my positive horizontal going this way. There's my positive x. To break down the velocity into components, we're going to be dealing with basic trigonometry. We're going to be dealing with sine and cosine. I'm going to take my diagonal here, my little diagram, and I'm just going to draw a right triangle on top of it, where the initial velocity is my hypotenuse. Right angle is right over here. Notice my angle is here. And my horizontal component I'm going to call v naught x. My vertical component I'm going to call v naught y. So horizontal component, notice it is along the adjacent of the angle. This means I'm going to use cosine. So cosine of my angle, cosine theta, is going to be v naught x over v naught. And if I rearrange this, I get v naught x is v naught cosine theta. Similar way, v naught y is opposite to our angle, means we're going to be using sine. So sine of theta is going to be v naught y over v naught, and if we rearrange that, we get v naught y equals v naught sine theta. And so these are our basic expressions for the horizontal component and the vertical component of velocity. These are, the point is not to memorize these, the point is to be familiar with how to derive them. And usually this is how you would derive them. Most of the time your angle is measured from the horizontal. Occasionally it could be measured from the vertical. So I could have, instead of my angle being here, I could have an angle like this. In which case you would either switch these relationships so that v naught is dealing with sine, and v naught x is dealing with sine, and v naught y deals with cosine. Or you could work your way to find the angle with relation to the horizontal. So you could say something along the lines of, the horizontal angle is 90 degrees minus the vertical. And then do the same kind of thing that we just did here with horizontal is cosine, vertical is sine. So working my way over here, notice I have my horizontal and vertical columns. And right now I'm using them just to kind of lay out the details of the equations and variables, that kind of thing. When it comes to working out the example, we're actually going to work out the example with these columns, with the horizontal work in one column and the vertical work in the other. Okay, so here I got v naught x, that was v naught cosine theta, v naught cosine theta, and my v naught y is v naught sine theta. Okay. So, finished with velocity, moving on to acceleration. And so, as was said in the previous video, because we're dealing with projectile motion means the only force acting on our object is the force of gravity. And likewise, the only acceleration felt by our object is the acceleration due to gravity. And because gravity works down vertically, we're going to be dealing with vertical acceleration is g. And value is 9.8 meters per second squared. In this video, we're going to be dealing with, we're assigning down as negative. And so here, this is actually going to be negative g for the purposes of this video, negative 9.8 meters per second squared. Because the only acceleration on our object is due to gravity, and that's completely in the vertical, this means that there is no acceleration in the horizontal. All our accelerations in the vertical, gravity, negative g, none of it is in the horizontal. The nice thing about this is this actually simplifies some of our equations. So if you notice here on the right side, in the vertical column, the uniform acceleration equations are the same as the previous video. We took our, make sure it's in the frame. There we go. Our uniform acceleration equations, notice here they are. Changed everything out. Delta x's became delta y's. We put our y subscripts on everything that needed them. Same as the previous video. For our horizontal component, our equations actually simplified because the horizontal acceleration being 0 cancels out terms. So, for example, here's the first equation, v equals v naught plus at. A for our horizontal is now 0, and this equation becomes vx equals v naught x. Conceptually, that should make sense because since our acceleration is 0, acceleration is the change of velocity over time. If our velocity is not changing, then our initial velocity should equal our velocity anywhere else in the problem. If you do this for the second equation, again, this term cancels out because a is 0, we actually get the same thing. Vx squared is v naught x squared, which boils down to exactly what equation or modified equation 1 says. And that's where this comes from. The third and fourth equations, same kind of thing happens. From those two we get this, delta x equals v naught xt, which is also vxt. When we cancel out acceleration, we're left with this equation, and while it's not going to affect how you do the problem, just a mental note, notice if you rearrange that, that is simply the definition of velocity. So when coming to do an example of these, again, vertical is going to be same equations as the previous video. Horizontal is going to be much simplified. We're only dealing with these two equations. When working with these, and with working with projectile motion in general, we're going to be asking more or less the same kinds of questions no matter what problem you're working on. It could change depending on the problem. Some problems like to ask for specific things, but in general, it's always the things that people usually want to know about when you throw a ball or launch something. You know, how far did it go? How high did it go? How long was it in the air? And so the common questions we're usually asked are for, how far did it go, its range, and that's delta x. How high did it go, or its height? And this will be some y in reference to something. For here, I'm going to write it as y max. And that'll always be when your velocity, your vy, the vertical component of your velocity, is 0. And last common question is asking for your time. How long was it in the air? And that is t. Now this last one's important because time is actually what connects everything else. If you notice here, the only variable that is common between this column and this column is time. Everything else is a component either horizontally or vertically. And so even when a problem can be asking for range or height or that kind of thing, you could be given information for range, for height, and they ask you for range, or vice versa. The way you connect values from this side and this side is by calculating time and bringing it over. And I'll demonstrate that in the example coming up. But just keep in mind, if you ever need to transfer from one side to the other, the variable that lets you jump between the horizontal and vertical components is time. T. So with that, we're now going to jump to an example. For example, we're going to be starting with something similar to the last video. Again, we're going to be standing on top of a 100-meter building, only instead of taking our object or rock or ball or whatever and dropping it, we're actually going to be throwing it. And we're throwing it at a speed of 10 meters per second at an angle of about 30 degrees, so that way. And we are looking for our range, how far it went, which is delta x, how high it went, maximum height, y max, and how long it was in the air, or our time, t. To start out with, I'm going to draw a quick sketch just so we can conceptualize what's going on. We are standing on top of a building, and we are throwing this thing at an initial speed v naught of 10 meters per second at an angle of 30 degrees, just theta. Our initial height is y naught, and that is 100 meters. So, as I said, initial height was y naught, 100 meters, and our initial x, horizontal distance, we're just going to be wherever we are, so 0. As before, taking our diagonal velocity and we are breaking it up into components, drawing out the triangle, and we got v naught y and v naught x. V naught x is adjacent to our angle, And so we're going to get that that is V naught cosine theta, which if you plug in the 10 and the 30 degrees, you get 8.66 meters per second. And same thing, V naught y is vertical. So V naught y is going to be connected to V naught sine theta, which again, if you plug in, is 5 meters per second. For acceleration, AY, because the only acceleration this object's feeling is due to the force of gravity, its only acceleration is the acceleration due to gravity, and so that's going to be a magnitude of g, or 9.8 meters per second squared. And since it's going down, we said down was negative, this is going to have a sign of negative. So our vertical acceleration is negative g, or negative 9.8. Because we only have acceleration due to gravity, which is completely vertical, our horizontal acceleration is 0. Okay, so now we have basic variables. We're now going to start figuring out what we can solve for. Notice we only have, let's see here, for a range, we have two things. You would think we need 3, except remember, now that our acceleration is 0, the only equation we're really dealing with is this one. We have our initial velocity horizontally, but we don't have time, and we don't have our range, which is what we're looking for. So we can't do anything in this column. So we're going to jump over here. We have our initial speed, we have our acceleration, and if we're looking for our max height, remember I said before that that means that our velocity, vertical velocity at our max height is 0. And now we have 1, 2, 3 things out of 5 we can solve for our max height. So coming over here, we don't have time, means we're going to be essentially using this equation. So we're going to be using Vy squared equals V naught y squared plus 2ay delta y. And from here it's essentially plugging in. Notice Vy squared is just going to be 0. So this is going to be gone. So we're just going to get 0 equals 5 squared plus 2 times negative 9.8 times the change in y. When you solve for that, you're going to get essentially that delta y is, see here, negative 25 over negative 19.6, which is going to give you 1.3 meters. Since we initially started at an initial height of 100, and we went up 1.3, our maximum height is going to be 101.3 meters. So there's our max height. 1 down, 2 to go. As I said before, we still don't have enough to find our range, so next thing we're going to do is find time. So for time, we want the time of traveling across the whole distance. So starting here, going all the way down to the ground, so that we get a final y of 0. So from here we have a delta y of negative 100, along with initial speed and acceleration. We have again 3 of 5 things to find time. Notice going along the equations, we don't have the final speed, so that's out. And again, we don't have the final speed, so the only equation we can use is number 3. So here we're going to be doing delta y equals v naught yt plus 1/2 ay t squared. And if you plug in, you get negative 100 equals 5t plus 1/2 negative 9.8 t squared. Okay. If you bring this 100 over, and I'm going to rearrange it a little bit, notice we are actually going to have to do the quadratic formula. for this problem. And this you can tell mainly because we have this square, and notice we have the form ax squared, or t squared in this case, so at squared plus bt plus c equals 0. If you plug this into the quadratic formula and solve, you're going to get 2 times. You're going to get a positive time and a negative time. So we're going to get a time of 5.06. And we're going to get a time of negative 4.04. For projectile motion problems, you can't really have negative time because that refers to the time before you threw the object. So we're going with the positive time of 5.06 seconds. Okay, so down, we got 100.3 meters, we got 5.06 seconds. Now to find the range. And this is what I was talking about before about using information from one side of components to find the other. Notice we had enough to find the range, we didn't have enough, we had enough to find the maximum height, we didn't have enough to find the range. We are now going to use our time that we got from all this information to plug in and find this. So delta x is going to be v naught x, which was 8.66, times 5.06, and that's going to give us a range of 43.8 meters. And there it is. We have found everything we needed. I want you guys to now try some of the practice problems that come in your worksheet after this example. Good luck, and if you have any questions, please let us know. Thank you.